Good morning, everybody. Welcome, the Zoom folks. I'm very happy to introduce our first speaker on site, Professor Rita Fioresi from the oldest university in the world.
That's what we claim. Sorbonne questions that, but
Okay, so you have a big
yes,
find who is the first. Okay, I believe that it is Bologna.
thank you.
Okay, and Rita will be full professor at the University of Bologna starting 1st of October. So
Yeah,
congratulations
thanks.
on hmm?
What?
I believe I started recording. Yes, I am recording. Why did you interrupt? It is recording.
It says,
But
it doesn't say it there, but it says it
it's
here.
here. So your interruption was unwarranted.
Okay.
But anyway, so Rita also at the University of Bologna, so seems to be very attached to the University of Bologna. She did her master's in, guess what, in nuclear engineering in the year 1989. So she's very weaponized. And then she did her master's also with distinction in 1991. But her real life started at UCLA. So we graduated from the same university in a way,
Yes,
right?
University of
Just different
California,
campus.
indeed.
And under the supervision of Vardajan, she earned her PhD in May 1997. Then she was a postdoc at UCLA under the year until the year 2000. Rita is a well-known expert in quantum groups and machine learning and Lie theory. Today, her talk will be focused mostly around quantum groups, and it's very well. It's worth emphasizing that Rita is extremely successful in getting funding. So currently, she's in charge of.
Look who's talking.
Thank you. She currently is in charge of a staff exchange network, which is something I also have. But she also runs a cost network and a doctor network. If you would say a few words about these
Okay.
projects, that would be fine, and then proceed with your talk. So anyway, welcome.
Thank you.
We are very happy to have you as our first on-site speaker. The site is yours. Take it away.
Thank you so much, Piotr and Eva, for inviting me here. This is a wonderful location, and we've been like really spoiled. We get excellent food, excellent surrounding, and it's perfect mathematical environment. As for the EU projects, I usually start my talks with that, but I figured that this time I wouldn't because of your presence. But let me tell you that if you don't ask for money, you're not going to get it. And I did ask, and no, it's true. It's like, and I got it beyond my imagination. And then I keep asking because who knows, right? And I advise you to do the same. In particular, since I am a recipient of two Marie Curie grants, one is a doctoral network, right? Another one is like Piotr Staff Exchange. We are more likely to be funded. Okay, so meaning that if you already hold such a grant, you are more likely to get another one. Why am I saying this? Because you guys are young. So you can apply for a Marie Curie postdoc and come to see me. Why not? Right? And you have more chances to get it approved because you are going to a place where it holds to Marie Curie. Same thing for Piotr, but I advertise me because in Poland they cannot come. You know, they have to go to a different country, okay? So when you apply for a Marie Curie postdoc fellowship, remember this: if you go to visit somebody that is already a recipient, your chances are higher. And for me, they're really high, like they're 50% higher than getting any other grant because they already have one. I know it's crazy, but it's like that. So the really hard point is getting the first one. Then the others are easier. But, I urge you to do that. All right. So after refill, it's really a great responsibility to keep going on non-commutative geometry. And today I will speak about differential calculus. So a bit of what is quantum Riemannian geometry. So that's the idea of this talk and how to define the notions that we know in differential geometry. There is way more than what I'm saying today, but I've been asked to be really simple in my talk. So let me show you the plan. So the plan is to explain my point of view on non-commutative geometry, which is less broad than what Professor Riffel said yesterday. He was giving you like a bird's eye view on everything, right? I will be more specialized. So being a smaller person, I have a smaller vision inevitably. So you'll be taken through, but it's true. I mean, what is it? It's like a reality. And in particular, you will see, so how do I like this thing? This, right. I will put my accent on homogeneous projective varieties. What are they? So you're taking a quotient of a group by a subgroup. So G mod P, okay? And you're looking at it as a algebraic variety and you try to deform it. I will explain. So we forget about the physical application, not because they're not important, they are super extra important, but my point of view is more mathematical, less physical modeling. Uh, and then we look at the structure, the construction of principal bundles and quantum principal bundles. Now there is Piotr here in the audience. I feel very scared because you are word expert in that, so you will forgive me. You already started asking me questions before the talk, Piotr. I can only imagine when I will arrive at that point, right? No, but
Wait and see.
no, but I'm looking forward. See, I really enjoy this dialogue. Otherwise, it'll be extremely boring. And then I will speak about the first order differential calculus. That is a very, so if you know something about Kähler differentials, that's what it is in the commutative setting. But actually, let me make it in a very plain explanation. This is exterior derivative for differential momentum. You have a function, you take df, the exterior. So it's very simple, and we want to quantize the structure. And then, of course, we put everything together and we look at the first order differential calculus on quantum homogeneous spaces and quantum principal model. So the last part of my talk will be putting together everything that we did from the beginning. I am not sure how much I will succeed in this very ambitious plan. We will see. And you guys are the recipients, so feel free to stop me in any moment. I'm joking with Piotr. Piotr is a friend. He can stop me and ask me in the corridor. But you guys have this chance now. So don't feel the least bit intimidated. Just ask me a question because this is not for the expert. This is for everybody, hopefully. Okay, after being taught, I didn't learn. Okay, so as for each topic, I will put down a list of references and also I will make my slides available, right? They'll be available. So you guys can go and of course I repeat myself, the whole story started with this beautiful book by Kohn where there is everything. But I wanted also to remember Drinfeld, which is one of the other big guys in the theory, and Faddeev, Reshetig, and Takhtajan. I'm taking more their point of view that came from integrable systems, the notion of R matrix, and I will take more the algebraic point of view of these three guys. And finally, Manin, that for me is the main author I refer to because the theory explained, it is explained very, very well in Manin's book. Not saying the Kohn book is everything, but Manin is more for what I do. Algebraic point of view on the deformations. Okay, so you, all right. So non-commutative geometry, I must have actually added the word non-commutative algebraic geometry. That would be more appropriate because non-commutative geometry is very wide, while I focus on a special subset. So I take an affine variety. What is an affine variety? It is something very simple. You are in some Euclidean space, for example, Rn or Cn, like the complex space. More is better the complex because it's algebraically closed. And you look at the zeros of some polynomials. So, for example, the parabola y equal x squared. This is an affine variety. Okay. And how you describe an affine variety? You describe it via its coordinate ring. The coordinate ring is just given by, the coordinates on your space. So in this case, x1 and xn. And then you quotient by an ideal. This ideal, you may say, oh, wait a moment, it's very complicated. No, it's very simple. The idea contains those equations that define your variety. So, for example, see, I have the possibility to write, is not a bad idea. Okay, let's hope. So, for example, in the case of the parabola, that will be c of xy divided by y minus x squared. Okay, so that would be the special example. And then you want to quantize this, and what does it mean? Very intuitively, we're going to make this more precise later on. You want to introduce a parameter so that when the parameter goes to 1, you recover the commutative ring. Okay, so I will show some examples, but you have a question because you are chatting. Or you're saying, thank God the bar is open today. That was the...
There are these mysterious brackets down X.
But you are impatient. So I'm going to slow. See these young people, they want to know more and more. Okay. So I put down some examples. Let's go to main example since this is the one of causing more trouble. So what are the little brackets? So this angle bracket mean that you're taking the tensor generated by. So if it becoming complicated, you may think that x and y do not commute. Okay, so in the commutative case, see you have this polynomial ring here or here, x and y commute, so xy equal yx. In this ring, on the other hand, xy do not commute, but satisfy the relation that is xy equal to q minus 1 yx. So when q is 1, they commute. Does it answer to your question? Okay. Manin like to take q as in an indeterminate so that you can make it equal to 1. But other people, many other people, take it as a complex number. So they fix it equal to some number. And when the number is 1, you get commutativity. Otherwise, see, Manin constructs what he calls the quantum plane, which is generated by two indeterminates x and y with the property xy equal q minus 1 yx. Then I also put the commutative, non-commutative torus, which has two generators that act on the function on the torus, but Riffel yesterday spoke at length about this, and I don't want to go again on the torus, but just to tell you that there is this relation, and similarly, the two operators commute when you take a certain variable equal, in this case, to 0, okay? So that is what we call intuitively, because of course, you would need much more precision that we're going to go in a moment, but non-commutativity somehow reduces to commutativity when you have some parameter set equal to 1 or equal to 0. Okay, so that's the bottom line. So far, so good, because if I lose you guys in the first slide, that's it, right? Okay. So what is a quantum group? Okay, it's impossible to give a crash course of quantum groups in 5 minutes, but let me try at least to give you an idea of what it is. So we replace, you see, before we saw we have an algebraic variety, for example, a parabola, and we replace it with this ring, which is essentially the defining equation. And for the quantum groups, the idea is the same. You take an algebraic group, we take an algebraic group and we replace it with this algebra of the coordinates. Then we call it H or we call it CG. And the idea is like you replace it with the function on the object. So if you have a group, you have two important operations, the multiplication and the inverse. Obviously, this is the definition of a group. In the function, is like a dual picture, like when you have a vector space and you look at the dual space. So you're looking at the functions. So you have a duality for which the multiplication is going from the algebra to h times h. So instead of going the other way, it will go, you know, dually. And similarly, you have something called the antipode that is dual to the inverse. And then you have the co-unit that is dual to the unit element. In any case, the thing to remember from this slide is that you have a group, you have equivalently an Hopf algebra, meaning you have algebra of functions of the group, and this algebra has all the information on the group. So a group or Hopf algebra is the same. It's called Hopf algebra because besides this definition, it satisfies many properties, but we don't care what are these properties now. They're not important. I mean, there'll be a complicated definition. The whole idea here is that you have an object and you look somehow at the functions on the object and you reproduce all the properties of this object, in the case a group, with properties of the functions. That's so it's a game, right? You try to do it. So the first thing that you like to reproduce is the concept of action. So if you know groups, you know that the action is an absolutely key notion. So,
Rita, would you allow me to jump in with a very quick
you're asking
comment?
me about actions.
No.
I'm very scared.
No, not yet.
Yes.
You see,
It's very intuitive, Piotr.
sure.
I'm hiding all difficulties.
Yeah. But I want to highlight one difficulty which should be maybe pointed at. You see, many things go very easily when you change your Hopf algebra H to be non-commutative.
Yes.
However, you have to, the troublemaker is Mr. Antipode, this S.
Yes.
Because when you write it like this, okay, I mean, it's still a pullback of the usual map between spaces, so it is an algebra homomorphism. But the moment you go into an uncommutative setting, this is an anti-algebra homomorphism. And the moment you're even more ambitious, like you go to quantum groups in the sense of Barnard, which is sister algebras and honest non-commutative topology, it's unbounded and
can become very complicated.
And becomes very complicated. This is why Bernoulli's definition of a quantum group is spectacularly different.
You are right. I'm trying to make it simple because you said it has to be captivating. But for example, it's not even obvious it is bijective.
No, of course.
So I mean, there are many hidden difficulties.
There are many beautiful properties. Like this was a stumbling block in quantum groups for quite a long time because when you take the inverse of the inverse, it's just the same thing.
Yes.
But it's not true with the antipode. The square of the antipode is not identity typically. And this was a stumbling block for many decades. This is why this birth of quantum groups doesn't go back to Katz. It goes back to Drinfeld. And
that part of the story I didn't know, the historical development. But let me go back to what we're interested. So if you have a group, you see you have what is called an action. So you have G acting on your variety, right? So you have Gx, G times X.
Oh no, so you're a leftist.
What?
You are a leftist. I'm a right-wing person. You act on the left. I always act on the right.
You left the right action. No, I will go to the right immediately.
Okay.
In the next slides, don't worry. I was worried. I thought you meant political orientation. I was very surprised. Okay. No, because in Italy we have right government in this moment, so it's. I thought he was making fun of that. Right. Okay, so as correctly Piotr remarked, you may have left action or right action. They don't commute, of course. Let me take the left because the right is absolutely the same. And as Manning did, Manning being the great man he was, he considered both actions, of course, at the same time. So you can have the co-action, the dual of an action, which is exactly this one. You have the dual going on the other side. So you start from the algebraic variety. In this case, you take your xy and we organize it in this way. So meaning that is a compact way to write it. What this really means is that x goes to what? To the product, right? A times, oops, I'm sorry, I cannot write it. Okay, let me just briefly say this is a compact way of writing that x go to A times x plus B times y. So it's a compact way to write it. And Manin asked himself, this will be actually my next slide.
Can I ask a question?
Sure.
About This is
not left or right.
tensoring over what? This CQG tensors.
Right. So CQ means that we are. This is a tensor algebra over the ring CQ Q minus 1.
But you tensor over what ring?
The ring CQ Q minus 1, the
Okay.
Laurent polynomials.
Okay, I
Right?
see.
Right. But if you are, this is the thing that people are disturbed by that because that's not a field. If you are disturbed, they can take Q as a complex number. That works. It will give you absolutely the same. So you'll be tensoring over a field and you're happy.
No, I actually felt
You
that.
prefer this one.
Yes, I
Fine.
preferred this one. That's why I asked. Because
Okay.
there was nothing below tensor symbol.
Ah, okay. No, because I know, of course. I mean, it's just my life will be shorter if I write all the symbols, right? I don't have the type, this kind of time. No, but you are correct. In order to be really precise, I should write CQ there. But being that the CQ, you can write it wherever you want because it's commutative, right? So it makes no sense to be, pedantic. You will write the balanced tensor product whenever it is really important that you have on the left and on the right. Otherwise, you don't write it. That's the common habit. Okay, but you are right. I like there are pedantic people in the audience. See, Piotr, you raise them well, these guys. Okay, so let's go. So Manin asked himself, what are the conditions that we should put on this CQG in order to have this well-defined? And as it turns out, Manin proved that you get back these relations that were discovered originally, but Fadeev, Reshetik, and Tatagian with different methods, the R matrix method. But I really like Manin's point of view because Manin is saying, you know what? I forget about integrable systems. I just ask myself, I have a quantum plane. I want a quantum group acting on it. What are the commutation relation that my variables must satisfy in order to have a well-defined coaction? And this is what Manin has done, reworking of Fadeev, Reshetik, and Takhtajan. And this is actually a good lecture for you guys that are young. Take the masters, read what they write, and try to rethink about what they write. This is always a very, very nice thing to do. So I personally have spent a lot of time on Harish Chandra and never regretted a single minute of it, but this is leaf theory, totally different representation theory. It's different story.
Sorry,
but I'm telling
I have a question, if I could.
not on Harish Chandra, I hope.
So the set of relations
Yes.
is meant to define this this quantum group, but
No. This is defining quantum matrices, and then you impose the determinant condition and you get a quantum group. You see, because if you just impose the 6 relations, you don't get a quantum group. You don't have a well-defined antipode. But if you impose this extra condition, this one, saying the determinant is equal to 1, then you get a quantum group.
okay. So maybe let me put my question
Yes.
in a different manner. So at the beginning, if you have written the CQ of G, it is at this moment before this definition is not defined. You then consider what does it mean to this object to coact.
Yes.
And then this definition somehow gives you
Yes.
not definition, this condition.
Manin, not me.
Okay.
Yes, of course.
This gives you this set of relations, and now you are using this set of relations in order to define this quantum group. Yes.
Okay, so you're trying to tell me this is like a wrong thing because we are using A to prove B and then B to prove A.
Maybe not wrong, but the motivation comes from that.
So you may say, oh, you know what? I define the special linear quantum group in that way, and then you say, hey, it works.
Yeah.
But Manin did the other thing. Manin said,
Okay.
what are the relations that come spontaneously from that? He also imposed the he imposed the action on exterior algebra, but I didn't want to go into it. So these are not enough. You need something else. But the idea is this.
Okay, so this story about this correction is the motivation for stating such definition, which
Yes.
otherwise would be artificial, yes?
But this definition was already known. That was known by Takhtagian, Reshetkin, and Fadeyev. These people did it already.
From
Manning
Baxter.
reworked it.
Yeah, they
Yeah.
knew it from Baxter.
Young-Baxter equation. Yes, the R matrix. Yes.
So yeah, I mean, this is exactly as you guys were saying. This is a reverse engineering.
Yes,
Reverse
exactly.
engineering, yeah.
And Rita, correct me if I'm wrong, but can't you get also like 2-parameter GL2 when you just demand
So
that it acts?
Manning wrote a multi-parametric deformations, but if you're asking me how he proved it, I read the paper, I don't remember it now, because I'm not one multi-parameter person. Yes.
So it is a solution, but it's not like the unique solution.
Possibly, you are correct. I don't remember that.
And another thing is, which should be mentioned, that you don't have to go to SL2. I mean, it can be
No,
GL2.
of course.
Suffices to demand that this quantum
Absolutely.
determinant, which is a group-like element, be invertible. Just adjoin the inverse.
Okay, so the other definitions would be, again, functioning by this idea plus some maybe possibly other relations additional.
You just adjoin the inverse. You just add it to the algebra. You declare that this animal AD minus P inverse BC is invertible.
Yeah.
Yes, for this SL2, but
no, for SL2 you put it equal to 1. For GL2,
okay.
Yes.
you adjoin the inverse.
For GL,
Okay,
you
okay,
invert
I
it.
see.
And it's really crucial it is central element, because if it's not central, you may encounter problems, okay? So, but it happens to be central. I will come to this question later on because we want to do localizations in a non-commutative setting, and this is going to be harder.
Okay, thank you.
Okay. So, but let's go to the homogeneous projective varieties. So I put down some references. Certainly, Arpin and Zhang and Rosenberg did very theoretical stuff, which I feel the need to quote. But to me, at least, they didn't give convincing examples in Lie theory and homogeneous spaces, but they provided some abstract setting. The paper that did actually some more ops. So it is Lakshmibai and Reshetkin where they really constructed, and then later on my work with Cicoli and Gavarini, that was in 2008, where we actually reworked part of this calculation. And there's also like Eckenberger, Kolb. So I am sorry, there are many people that worked on this, and I just put down the ones that I wanted to, just highlight. But if you go to the Cicoli Gavarini paper, you see more references. Now, what is the setting that we want to take to consider? So we take a complex, semi-simple algebraic group, and despite the scary, all these adjectives attached to a group, SL2 is an example. And if you know something about Lie theory, there are not very many of these. There are 4 big families, which are the orthogonal, the symplectic, and the special linear. And plus there is a bunch of exceptional ones. So you are
you see, Rita, at this moment, your talk is no longer simple, it's only semi-simple.
Right. No, come on, you can think about SL2 and you'll be happy. You see a lot of examples of SL2. And then we take, I define a CG. Oops, I want this.
You're okay. Very creative with the bunch.
Yes, I don't know what I'm doing. Now I'm a bit worried. Okay. And then we take a closed algebraic subgroup of G that I call parabolic. And again, this is not a big deal. So, for example, the parabolic is like upper triangular matrices. For example, you take SL2 and upper triangular matrices. That'll be an example. And Lie theory is interesting because everything is very, very explicit. So I love it for that reason. And then we fix a character of P. So it's like a group homomorphism from P to C star, the invertible elements in C. And if you know something about representation theory, characters are very closely related with representations. But if you don't worry about that. I'll try to keep it minimal. Then we need some algebraic geometry. And again, I promise to keep it really minimal. Because what you want to do is you take your projective, you take this, because you see,
What is IP?
yes,
Your quotient over IP.
yes,
What is it?
okay. Thank you for stopping me for not being precise. So if you take a closed algebraic subgroup, there'll be an ideal defining it. So that's the ideal of the relations. So this is actually something extra super simple. So I'm glad you asked. So for example, if you look at ABCD, right? And you look at P as the upper triangular matrices, these upper triangular matrices will be defined by the ideal containing C, because that'll be all the matrices with C equals 0. And to be honest, we're looking all these big words, but actually it's going to be like that all the time. So you can prove that parabolic is really like something which is like a little stair. So some coordinates are 0. So see, we are like scam, Lie theorists. We make a complicated thing for something very simple. Right? For parabolic, for sure. Okay, and then we want to look at the algebraic variety G mod P. You see, this algebraic variety, so if you take a quotient of a group by a closed subgroup, you get a differentiable manifold. You also get an algebraic variety. The problem is, well, not the problem. The fact is that if P is parabolic, like the one I described, what you get is not affine. So you get something projective. And being projective, there is no ring associated with it. And that's a big deal, because if you're doing non-commutative geometry like I do, you like the coordinate rings, because you remember the thing we said at the beginning. We said, oh, you have an algebraic, you have a geometric object, a variety, a group, and you associate the ring of functions. Well, if you have a projective object, there is no ring of functions, so you have a problem. What do you do, right? So if you take the projective space, what do you do? And of course, what I'm telling you now, it's not what I did, because this was very well, for example, Landy School and other people. I probably say the wrong attribution. Who did the quantum projective? I don't know. Many people. It's difficult.
Well, actually, the first reference to
Yes.
quantum complex projective spaces is very ancient.
Yes, I'm
Done
sure.
by some physicists, and it was
Yes.
done ages ago.
But what we've been trying to do with my collaborators, Ciccoli and Gavarini, we've been trying to think of a mathematical way to soundly define it.
But you know what? I would attribute it to Waxman and Soibelman, because
Possibly,
they did
yes.
these quantum spheres, and when you have these odd dimensional quantum spheres, take fixed points about you, and the U1 is so trivial.
And in fact, I quote a Soibelman, so I'm happy I gave. So later on, I give the correct attribution. So what we've been trying to do is reread these papers and understand in a more conceptual way. So the idea is the following. In order to embed a projective variety into a projective space, you need something called a line bundle. Don't worry about that, because if you know projective geometry, fine. If you don't, you have this device where will give you this embedding. And the ring that you obtained is through this embedding. So you may think, well, wait a moment, Rita, you told us there is no ring. No, I said that if you have an affine object, so if you have an equation that define your object into a vector space, then you have a coordinate ring and there is a one-to-one correspondence. The information is one is exactly containing information of the other. But if you have a projective variety, you may associate a ring, but you may associate more than one ring. So depending on the projective embedding that you choose. So different projective embedding, different non-isomorphic rings. So you really have a choice there. You have in tandem deformation, where you have your variety, you have your embedding, and then the ring coming out like that. And if you know projective geometry, you know that in the projective space you have a grading. So you take homogeneous polynomials. So this coordinate ring will be graded, and you need to tell me what the grading is. And in fact, we give this definition. This is a relation also with Eckenberg and Kolb. This is a bit technical. Bear with me. It's not like so crucial in the sense that I want to give you a very concrete example that will make you feel more, down to earth.
Let me ask you a very stupid question. So you have this projective embedding of G mostly
Yes.
in what? Where do you embed it?
In some projective space.
In some projective space, like complex projective space.
Maybe the example will help.
Okay.
Okay, so
Sorry,
because the can I show the example? Then you ask me, keep your question and then ask, okay? Because I think it will help. So let's take a very concrete example. So we take SL2, as we saw before. We take parabolic, which is the upper triangular matrices, and we take the projective space, which is SL2 mod the parabolic. If you know how this is realized, and not so crucial now, I think it is safe to assume that we all know that the ring of projective is the homogeneous ring in two variables, right? That we know. Graded ring in two variables. How do you obtain this ring with the recipe I described? So you fix a character. For example, you associate to the matrix AB0DA, that's a character. Then the recipe says, look at all the functions that I denote with A hat. So the function A hat associate to a matrix the first element up. And this function is exactly doing what is prescribed to do. So it's chi, the matrix, times A hat, the function. And this will tell me that the ring, the graded ring is generated by A hat, but also C hat. So what I'm trying to say is that the recipe I described above will recover the homogeneous ring inside the group generated by the element A and C, meaning the function giving you A, the function giving you C. So we devise a recipe to do this. What is the question?
yeah, maybe stupid and technical question related to the previous slide about the minus sign. You denoted your grading by n, but if this n is equal to 1, you also put...
Yes, I know, the minus one. This is the curse on left and right. So if you want left action, you need a minus one. If you want the right action, no minus. So, and I'm so bad that in the same slide, I put a plus and a minus, but you taught me very good.
Okay, thank you.
No, because you see, with the minus one, you sort of switch left with the right action. But thank you. This was like, I should be more careful. I'm not careful because I'm an engineer, right? All these
But a nuclear one.
Huh?
Nuclear one, so you know everything
Nuclear.
about nuclear sister algebra.
But given the international situation, this gives me a job, no matter what,
absolutely.
right? So, no, you are joking, but I receive offers and
Really?
from African countries, yes, indeed.
Okay, okay.
Yeah, because they don't find the Western nuclear engineers paying attention to them, luckily, for now. Okay, so let us look. So the important thing to bring back from this slide is that we have a very concrete way to realize the homogeneous ring of P1 inside the ring of the group, which is kind of a miracle, this thing.
So by embedding, you mean embedding rings or
You embed.
embedding of rings, actually, not
Yes.
spaces? Okay.
No, even
Okay.
more. You see.
Okay.
You see even more. Okay, so it is now for the commutative, and of course, all of this can be generalized to what is called the Grassmannian. And again, this slide can be a little mysterious if you never heard of Grassmannians. This is a generalization of projective space. So if you remember what is projective space, are the set of lines into some vector space. And Grassmannian, instead of taking the lines, you're taking two-dimensional, three-dimensional space. Yeah, the minus one is still there. Adam, forgive me. It depends what you want to
I'm a
put
little
it
bit
on.
confused by this number 4, but now I presume that A, B, and D are 2 by 2 matrices.
Correct. I was going to say it, but you guys have to see. You totally fooled me. These guys are very fast. I am the slow one here.
But it's just one person.
One. Okay. No, but they're very smart and fast. Okay. So all these letters now are 2 by 2 matrices, correct?
You see, Rita, I pay him to ask questions. So
That Your money is well spent, I can tell you. All right. So, and this time, instead of taking just the element A, you take the determinant of the matrix. And if you build what are the recipe that we gave in the first slide, you obtain all the determinants. Now, if you know something about projective geometry of Grassmannian and so on, you immediately recognize the determinants as the coordinates of the Plucker embeddings. This is something of classical geometry, and indeed, these are the Plucker embedding. So this slide is just to tell you that whatever we do for projective, we generalized to more complicated Grassmannian flex and so on. Okay, so essentially this proposition tells you that this recipe that I described to you explicitly can be replicated in a very generic way. So if you get a G mod H, which is embedded in Pn, we saw the example of the projective, I hinted the example of the Grassmannian, you can do it for any G mod H. And this recipe will give you the projective embedding. Oops. Will give you the projective embedding. Will specify this ring O G mod P. Why don't I call it C G mod P? Because this I indicate with O because it's more like sections. It's not functions. Depend on the embedding, not intrinsic, and are homogeneous. So they are really now. If you are an algebraist, you immediately see that this definition, I do always the wrong things. This, I don't know what I do.
You're probably pressing a button in the pen.
Ah, thank you. Okay. Okay. So if you look at this definition, you see that this OG mod Pn is already prepared for the quantum group setting because it uses co-multiplication, it uses the projection of rings, so it is ready. And in fact, we replicate it in the quantum homogeneous setting. So let me have like a small slide to put a bit to context. What do I mean with quantum group? What do I mean with quantization? So for me, a quantum group is an algebra over this ring CQ, which is CQ, Q minus 1, the Laurent polynomials in the indeterminate Q, which has the property that when you quotient by Q minus 1, so you do this operation, okay, I didn't press anything, I did it for me.
Okay, now it works.
So when you quotient, you obtain the ring of the group itself, and you want the torsion freeness condition. This is a condition that tells you it behaves nicely. And then you say that OQ is a quantization of the ring of a variety if it is torsion free and it reduces to OX when Q is 1. That is.
And can you say what do you mean exactly by torsion free?
Well, torsion free means that if you do, okay, I will write it in mathematics. So A times M equals 0 or.
Okay. Okay. Yeah.
That is the torsion freeness condition. Okay. Now it's just you have a so it's a little milder than non-zero divisors. It's a little milder. You don't want the scalars to do anything wrong.
And you don't want it to be faithfully flat.
What?
Faithfully flat.
So torsion free is somehow related with fate of flatness, right? Ah, so it was an exam. The one. No, these are a bit technical condition. Torsion freeness, I think, is a little milder than fate of flatness, right? So, but if you ask me to produce now on the spot a proof of one or the other, I wouldn't know. Okay, so I declare incompetence. Now, OQX is called the quantum homogeneous variety if it has a coaction of the quantum group. Why are we interested in that? Because if you look at this condition, just this one, this is, this one, this is very mild. It's a condition that anything can do. But if you ask this extra, admits a coaction, we go back to our friend Manning that, told us that this is a very restrictive condition, that actually starting from variety gives you the group or vice versa. So it's a very strong condition. And so for this reason, we are hoping to get something. And especially in the theory of quantum groups, the problem is not definitions and theorems. The problems are examples, am I right? Because you can prove many things, but then if you prove and then you have no examples, what are you doing? For me, you're not doing mathematics. That's my personal opinion. Some
I
higher
could not agree more.
Eh?
I could not agree more.
Yes, but I think me and you are a part of a family. There is another family that thinks they can do whatever, but no, not me. It's just okay. So we reproduce this technical condition that I call quantum section that allows you to build this the coordinate ring of the embedding of G mod P. So you take G semi-simple algebraic group, you take P parabolic. Remember your G is SL2C. In the example, your P are the upper triangular matrices, and G mod P is the projective line. So very down to earth.
Rita, I have a question. So on your previous slide, you said that you call something a homogeneous space when it's has a coaction. And I think like classically, the action has to be transitive, right? The definition of a homogeneous space is that you have an action that is transitive. So are you assuming this here? Or? No, okay.
No, but
well, you have it in examples.
Okay, so you are correct that I should be more careful in the definition, because if I want to be quantum homogeneous space, you are right. We should have something. But truth is that in our setting, in my paper, I start with G semi-simple, P parabolic. That's automatic, right? Because that's a symmetric space. It will have it. But you are correct. I wanted to play smart and be more general, see what happens. So no, you are absolutely correct. Yes. Okay, so let's go back to this. So we have a way to determine OQG mod P as a sub-ring of G. Precisely, see, here it shows it clearly. We take the function on G that has a certain behavior, but it is more than just a subring, okay? So it has very nice properties, and the theorem with the Ciccoli and Gavarini clearly shows it. So let me show the theorem because I'm running short of time. So this theorem tells me that not only it is a nice graded ring, but it has automatically a coaction, and this coaction is the co-multiplication of G, of the ring of G, restricted to that subring. So it is very surprising. At that time, with Gavarini and Ciccoli, we were very happy, and we published our paper. What we did not realize at that time is that we were holding the key for the quantum principal bundles. And neither of us, and I mean, Gavarini and Ciccoli are no young flowers, right? But we didn't see it. So 10 years passed by and we were happy with it, living our lives. But then, you see, there is a very super important example of principal bundle, which is the projection of a group G on its quotient, G mod P. Okay, that's like a prototype. In fact, if you're doing something called Cartan geometry, that'll be like the prototypical example. They study a lot. And what we didn't realize with Ciccoli and Gavarini is that the quantum section was holding the power to do this. And this came much later. Okay. Let me skip on the examples where I wanted to show. And by the way, I put down Seibelman as I see Seibelman as initiator. So I will skip these slides of examples to talk about the principal bundles and quantum principal bundles. So most likely I will not be able to speak about differential calculus, just the last slide, but what can you do?
Yeah.
I prefer to be clearer than...
You're absolutely right.
Yes, instead of...
quality, not quantity.
Yes. So principal bundles and quantum principal bundles were really like a very hot topic in the past 10, 20 years. And the work by Beggs and Majid, I'm not saying that they are involved. I'm just saying they wrote a paper, sorry, they wrote a book of what, 800 pages. And if you go in that book, you see some reference because these guys are not giving full reference, but that's okay.
But Rita, you skipped the second dot after my second name.
Oh
There's
no,
no
what did
dot
I?
after M. You see, it's PM, but there is no dot after M.
Ah, I see. I knew you were a perfectionist. Okay, we'll send you a revised version of the slides.
Thank
But,
you.
but in any case, what I'm going to tell you right now is based on my work with Aschieri and Latini, quantum principal bundles of a projective basis. Because all of these guys here, what they've been doing, they've been looking at principal bundles over some objects that are affine, okay? They were never treating the case of G mod P, where this is projective. The reason being that doing the quantization, they're quantizing the ring, while you cannot for projective. And that is what we've been trying to do, and we did. So the way we did it, we first of all, let me remind you what is a principal bundle. So you have two algebraic or differentiable manifolds. You have a projection map, which is, of course, differentiable. I didn't say it, but of course, and it is surjective. And then you want an action on the right. You are happy with that, of course. No, you must. And it must be acting transitively on the fiber, okay? And then you have that E is locally trivial over M, meaning that your total space will split as M times some Rn, okay? Something diffeomorphic to it.
Now, if you allow me a
yes,
very
please.
brief historical remark,
Yes.
because the original definition of a principal bundle done by Rita was not locally trivial, and I kind of don't.
Henri, not Eli? Henri?
No, Henri Cartan, yes. This was, I don't remember the year, like 56, and he defined it in a way which was like a prototype for Hopf-Galois theory.
Ah, look at that.
And because you see, non-conductive geometry in terms of sister algebras is inherently global.
Yes.
It's very non-local. Quantum mechanics is non-local. Non-conductive geometry is non-local.
Yes.
And also even local triviality of principal bundles. I mean, to solve it in the context of sister algebras, it was Marius's thesis. It was a very long-standing problem because doing honestly open covers in non-commutative
No, you are right.
sister algebras.
So what you're saying is that this may be too much to ask.
Yeah, we have very natural examples. These are not pathological examples which you fail to be locally trivial.
Yes, but the truth is that if you're looking at homogeneous spaces as we are, G mod P, you have it. So it's like, for us, it's a fortunate situation, but you are correct. This can be removed.
I mean, if you have the context of Lie groups, you're always locally trivial because of the Glisson and Palais.
No, but the surprising also if you have algebraic groups. In algebraic groups, different from Lie groups, Lie group, when you go to G mod H, you have local triviality of this bundle, G mod H. In algebraic groups, not always the case, but for G mod P, the case.
But you see, the context in which local triviality fails actually is the context of totally disconnected spaces, so like p-adic integers.
Oh God,
and in the context of Hilbert-Smith conjecture and stuff like this is exactly what we do.
P-adic outside myself. But I must tell you that for Varadarajan, that was very important. He thought p-adic numbers were something to consider because of disconnected nature. And he said,
Dorset-like things, you know. Basically.
He said, he was saying to me, there was one of our last conversations that the microscopic nature of the universe may be p-adic, even at the lecture about that. But he never convinced me to study p-adics. I don't like them. I like complex. I like it. With complex numbers, your life is easier, right?
True that.
Exactly.
Sorry, could you repeat who is this remark about this p-adic?
Varadarajan.
Okay.
And not only the remark, I can send you his slides. They're very inspirational, where he said that space-time should be p-adic nature.
Oh, I would be interested.
And I remember also talking with Bob Finkelstein, that you may or may not know. He was a collaborator of Einstein. He was explaining this to me. I was so fortunate to hear it from Bob. He died like during the pandemic. He was 103 when he died. And for me, it's like a privilege of having talked with somebody that collaborated with von Neumann and Einstein, right? This is like big, big names. But he also was convinced of that, of the disconnected nature in the infinitesimal physics.
Yes, but saying that it is actually periodic is more, I would say.
I know.
And
but you are asking me, and I'm the wrong person.
Okay,
don't know about periodic, don't know about physics. So it's really like.
But he really believed in the statement, yes?
Varadarajan? Varadarajan, yes, absolutely. He even wrote papers about that because he felt that you needed to know how to integrate. So he wrote papers about to do analysis on this. You are checking it on the internet, so it is true. I know.
But not ChatGPT, no?
Huh?
No, not ChatGPT.
No. And Bob Finkelstein, I'm less sure about what he meant, but when he was 100, he wrote this paper that was published on JMP. You may check that. I mean, physicist, I trust more Bob because he's like a physicist on inner core. Varadarajan is very, very good, but more mathematician. Okay, so the two people, they're like gigantic, but different realms.
Yeah, but the immediate question is this exact value of P, since you have periodic for every P. So which P should be somehow distinguished in nature? I don't get it.
It was him. Ask him. It was him taking.
Explanation.
We can have this talk sometime else. I really have no expert in periodic. I really don't. I mean, I know barely the definition, right? And when they tell you that neighborhood are at the same time open and closed, that this is where they lose me, right? Right at that statement, they lose me. Don't laugh. I mean, I'm like a complex person, very easy life, and so on.
We are a complex person. Okay. Okay.
I am.
I've got your point. Okay.
Yeah. Algebraically closed life is easy. But in any case, what we've been trying to do, inspired by Flaum, is that, okay, we want a principal bundle. We want a sheaf on H commodule algebras. Commodule is the dual module, so that you want a local triviality. And I totally understand that Opfgalois is more
global.
Is more global, and perhaps we also have, because it's paper with Aschieri, so he really demanded the two versions of this definition, one with the local triviality, the other with the Opfgalois, because he knew. But I don't want to get into technicality, because if we start the Opfgalois business, we're finished. So, and let me, since I'm really running out of time, let me skip the examples. And let me give you just the main result because of this part. Okay, so with the Aschieri and Latini in 2021, we successfully built an assignment that assigned to open sets some ring, so a sheaf theoretic, so that we obtain a quantum deformation of the principal bundle G over G mod P, okay? So we obtained this. There were many technical difficulties. The first one is to find out what are the correct localizations, because of course you are in a non-commutative setting, so it's not that you can invert whatever you like, no.
Allow me to jump in here.
Yes.
This is what I would call sheaf theoretic approach, because by doing localizations, we are really talking open coverings. Flaum is doing closed coverings. This is why in this context, sheaf is just a
yes,
joke.
I think you are totally right. I should say Flaum inspired, not
Inspired.
Flaum inspired.
Let me, because it's very important. A huge discovery of Marcus, but remember, it was 1994, it was really pioneering, okay? Was that he discovered what is the correct notion of a trivial bundle, because people try to do it earlier. They said, okay, so take the tensor product, but this is completely wrong. You have to take the cross product. True. And it was a big discovery of Flaum.
I didn't know, was him?
Yeah, wow. Because he said, okay, so I will try to do it piecewise trivially. He didn't call it piecewise trivial, but if you are localizing over a closed covering, not open covering, it's piecewise trivial, not locally trivial. And with Paul Baum, we have an example that two notions differ.
No, they are different. Yes,
exactly. I mean, you can be a piecewise trivial without being locally trivial, but not vice versa. The point is that he was doing interesting instant bundles. So his structure group was SUQ2, it was really a quantum group. So there's a lot of non-trivial non-commutativity involved. And then it turned out that when he puts it into pieces, where normally the instant bundle would trivialize over contractible spaces, it must do so. Then he could not combine two tensor products. I mean, he had to use really cross products. This was somehow imposed by the global structure. But then cross products, when you are commutative, are tensor products, and then you have a trivial bundle. So this was a huge discovery of.
I didn't know it was Flaum.
Yeah.
Okay. Yeah. So I will tell Landi, wait a moment. Yeah. This Flaum guy is something.
No, I mean, that was remarkable.
So because Landi, when I was giving this talk, said, oh, you know, Flaum didn't have anyone following him, actually. And this is not true.
This is not true, because he actually, before Flaum was Budzinski-Kondratsky, but he gave a wrong definition with tensor products. And then he kind of finished it off, giving a concept of piecewise reality in full generality. But this is for closed coverings. This is suited for sister algebras. You're doing honest sheaves and non-commutative algebraic.
Yes. So let me tell you what is the point here, is that in our treatment, we cannot afford for our examples to look really at open covers as we think for differentiable manifolds, even for algebraic varieties. The reason being that you cannot localize a lot. So we do a finite open cover. And we look at the sheaf defined on the topology generated by this open cover. So this is a very strange topology because it's a finite topology, right? So you may think now, oh, wait a moment, you have projective space, you have a finite topology. So for example, for P1, it has three sets, U1, U2, and the intersection. So this is a very false topology. But with my collaborator now, we're having a paper that was due when I was giving the talk, but it still has to come out, where we prove an equivalence of categories, that you have actually, if you take schemes with some mild properties that allow for any cover, this category is equivalent to looking at sheaves with finite. Okay.
And you mean in the classical setting?
Yes.
Okay.
In the classical setting. But then this motivates, saying, you know, now we are fine because we are doing that. Now, this paper was about to go out in July. We find a little error, as it is in papers. So, guys, remember, read your paper 100 times before posting out in the archive. We discovered a little error that made the paper, 10 pages longer to fix it, as it is normal, right? And so I was left with, there is an equivalence category that we are using here in 2021, but the paper justifying it is yet to get out, right? You say like that because you know how that is, right? Okay. So I guess that now I was supposed to give examples and differential calculus, but since you guys stopped me a lot, I guess that there is no time. I thank you very much for the attention. Let me go to my last slide because I really like you when I say thank you. This is the last slide. Thank you very much.
Thank you very much, Rita. Give me a high five. This is good.
Thank you, Piotr.
Okay. Thank you very much for such a very, very inspiring talk. Maybe first we'll try to take some more questions from the room.
Get a lot of Marie Curie postdoc, who knows, in Bologna. Come.
Anybody? Go ahead.
May I?
Sure.
So what is the relation between this more algebraic theory with quantum groups as defined by people doing operator theory? Because they use the same name, quantum groups.
Piotr, this is a question for you.
Okay, it all depends whether you are compact or locally compact. When you are compact Hausdorff, then this is a beautiful Vonovich theorem because Vonovich developed Peter-Weyl theory for his compact quantum groups, and when basically it becomes the theory of co-semi-simple Hopf algebras. Okay, but the situation changes drastically when you go to locally compact groups because not only you are not only that your sister algebras are not unital, but your generators are unbounded, and you have to have always fear of affiliated operatives and generating sister algebras, and it becomes way more involved. So by the sheer fact that what Rita is doing, she's doing this localization, that's something which is a very big no-no in sister algebras. You see, you have divergent point of views of algebraic geometry, where you say, okay, I have polynomial rings, but I have many of them, and I have sheaves of rings. Okay, and in sister algebras, you say, okay, I mean, we have just one sister algebra, and it's a global one ring to rule them all. I mean, it's non-convex geometry by sister algebras is very, very global, and Marius can attest to it that when you try to do honest to God local trivialities in sister algebras, this was a big breakthrough, because it was a standing open problem for like 2 decades. How to address what on earth is open cover in terms of sister algebras when you really want to have this Gelfand-Naimer correspondence. You see, this is what Mark was telling you yesterday, that you have this equivalence or anti-equivalence or contravariant equivalence categories. So in principle, everything should be expressible. So when you restrict yourself to commutative sister algebras, you should get really this locally compact Hausdorff topology. But it's some concepts are very tricky to express in terms of sister algebras, like the antipode. I mean, there's sort of the genius of Aronovich to define the antipode in this context, because you cannot use this whole algebraic approach. But when you are compact Hausdorff, which is when interesting topology for principal bundles happens, then it's cosine-simple whole algebras. And this agrees with that.
So I also wanted to add that our paper, I think it contained this part which is theoretical, but it was mostly liked, I think, because of our examples, where we were able to construct the projective space, PN, using this shift theoretic method, right? And you are inverting elements, and you have to show they satisfy something called the OR condition, which was a bit technical. So I remember myself in July, it was very hot in my house, you know, sweating and computing all these things. You know how that is, right? So I'm telling you that in order to build examples, it costs, I mean, it's not simple at all.
You need air conditioning to build examples.
Eh?
You need air conditioning to build examples.
You need air conditioning, yes. Okay. More questions?
Any other questions?
Maybe a little bit like a follow-up question. So in this context of operator algebraic quantum groups, there is almost at the start, okay, maybe not at the start, but very easily you can obtain some representation in Hilbert space. And in this algebraic context, I don't see Hilbert space at all. So
yes, I said it at the very beginning as my disclaimer, saying that as much as I love the Rita talk yesterday, we are taking a much narrower point of view where we're not bothered by, you know, asking for representations. And people doing what we do, actually, they do now. Also, you, Piotr, when you write your papers about quantum principal bundle, you're not building representations.
Yeah, but we are using sister algebras, so we have representations anytime.
I see, perhaps.
Oh, no, but still, is there any easy way to obtain some Hilbert space context from this stuff or not?
Well, I mean, ask the same question for classical algebraic geometry. Take classical algebraic geometry schemes and tell me where are Hilbert spaces in the theory of schemes.
There are no.
So
it's very difficult. But okay, we're playing a game that you know, people doing what we do, they're not asking for that. So we somehow lost the physical motivation, and we kept going without you know. But I understand what you're saying. We're not doing it.
Yeah, but still, even not going so far to physical applications, still, if one is interested only in mathematics, one could be interested in Hilbert space. But okay, I believe that there is no hope to obtain this. Okay, thank you.
Okay.
Anybody else?
The online
Anybody from the Zoom? Hello, 25 guys.
They're all sleeping. What do you?
Everybody is asleep.
Let me check if my students are there, because if
okay,
they're not,
who is your student?
Okay, let me see. No, I don't.
Marta,
see.
Don't you have any questions?
No. Ah, let me see.
I know.
They're not there. Look at that.
So you cross them out of your doctoral network. Okay.
No, wait. They will get it from me because I said you have to attend.
Okay. No?
No?
Shame on them.
Really? Okay.
Okay. So in this case, if there are no further questions, let us thank Rita.
Hello, I have a question.
There is a question,
Go
perhaps
ahead.
my student.
Agnieszka, go ahead.
Yeah. Suppose, so you said that algebraic groups acts on algebraic variety in your first slide itself. So does it always induce a coaction on the coordinate ring Cx?
Yes. So you're asking me if what we produce always has coaction? Yes, it does. It's part of our definition, and we prove that in our. So let me show to you the theorem because you are right. I went very fast over the result. Right. So in our theorem, we say that the assignment define the sheaf of CQP comodule. So there is a coaction on each of the open sets, right?
Mhm.
So yes, the answer is yes. Is this your question?
Yes, thank you.
Okay, yeah, it's part of the theorem.
Okay, thank you.
Anybody else? Okay, I don't see any raised hands. So, all right. In this case, let us thank Rita again for this very, very inspiring talk. Thank you.
My pleasure.
And our next speaker is Professor Coffee Break.
It's coffee break. Yes, I was wondering about that.